Hi everyone, thanks for coming out. I'm delighted to be hosting a talk by Václav today. Václav is a PhD student at ETH, but his advisor moved to MIT, so he's visiting MIT for the year. His advisor is Mohsen Kafari. He has many sort of like state-of-the-art results in theory, including, and I wrote these things down, the fastest exact single source shortest path parallel algorithms running in depth root n, the fastest approximate single source shortest path parallel algorithms running in polylog depth, as well as the first deterministic polylog time algorithms for distributed constructions of something called network decompositions, which is some kind of like very important tool in distributed algorithms. He's also like the closest thing you get to like an influencer in TCS, I guess. So he's like written papers with famed mathematician Terry Tao, and also jointly runs a YouTube channel, Polylog, whose most popular video has 2.4 million views. So he's like, you know, famous as famous gets in theory. So with that, I'll let him.
Actually, Alice forgot to say the most important thing, that my Hershkovitz number is 2. Yeah, but actually today I will be talking just about Dijkstra's algorithm. Okay, so it will also be like a Blackboard talk, and I actually like hope that I will deliver not just vibes, like but like actual theorems. So let's actually just and it's also joint work with Bernard Heupler, Richard Hladík, Bob Tarshan, and Kuba Tětek. So let's actually start by recalling Dijkstra's algorithm, right? So also please, like, whenever my writing is too bad, or whenever you want to ask anything, please just ask, right? There are not that many of us here. I don't even know how to write it. Like this, maybe. Dijkstra's algorithm. Right, so first of all, let's talk about like what is the problem that this algorithm even solves, right? So we always say that it like solves the SSSP problem, like that it finds the distances, right? But it actually solves like a bunch of related problems. So what does this algorithm solve? So it kind of computes the distances, right? From a single source to all of the other nodes. It also computes the SSSP tree. But actually, for this talk, it will be important that it also computes like one more thing, and this is what I will call distance ordering. Okay, so let me explain what is distance ordering. So if you imagine that you have some graph, some source, and you are running Dijkstra's algorithm, then basically this Dijkstra's algorithm is kind of closing the vertices in some order, right? And this order is like what I call distance ordering. It kind of like sorts the vertices based on their distance from the source, right? And this is kind of like a trivial problem. Like if you know the distances, sure, you can just like sort them, and you get the output to distance ordering. But it will be actually like very relevant problem for our discussions. Okay. So now let's talk about the complexity of Dijkstra's algorithm. So as we all know, like the complexity, if you just run it with normal heap, it's just like m plus n times log n. But that's not the best possible, right? You can run it with Fibonacci heap, and then the complexity becomes O m plus n log n with Fibonacci heap. Right, and when I heard about like this Fibonacci heap algorithm for the first time, I think the teacher also said at the end something like, "Oh, and you can see that this is like kind of the best possible, that like this n log n cannot be improved." So like, do you also have this kind of feeling that like this n log n cannot be improved? Or yeah, that was a question.
Here, what do m and n correspond to, like vertices?
Oh yeah, m is like number of edges, and this is number of vertices. Yeah. Yeah. So can you like say like in which sense this is like the best possible that you can get, this like complexity m plus n log n?
So I'll take a guess, but if you could improve it, you could somehow get better results for sorting.
Yeah, exactly. Like basically, like kind of the example that you can think of is like some kind of star, where you have the source and then you have like a bunch of other vertices. And now, kind of, it's important that this Dijkstra's algorithm is actually solving not just the problem of computing distances, but actually like ordering the vertices based on their distance, right? Which means that like if we are talking about a distance ordering problem, then like solving distance ordering problem on this particular graph, on this very particular graph, actually solves sorting, right? So like this is the sense in which you cannot improve this n log n complexity, because if you could solve this concrete problem on that graph in faster time, then that would break lower bound for sorting. And you also we also need to be careful because we need to talk about like what is the model in which we are in. So there has to be some kind of like comparison model where we are allowed to only like compare stuff and maybe like add two things together. Okay, so it's like best possible. Let me write it down. Like best possible. Okay, but actually what this talk is going to be about is that we are going to improve it, or we will try to improve it. We will try to improve. Okay, so that's weird, right? Like we have like a problem, this distance ordering problem. We have the best possible algorithm for that problem. Still, we are trying to improve it. So like clearly, we cannot be looking at the problem like with the lens of like worst case complexity. We need to kind of like go beyond worst case, right? So that's what I will talk about right now for a few minutes. Let's kind of talk a bit about beyond worst case analysis. Right. So actually, I think I should have. I should have something prepared here. Oh yeah. So this is like a famous book of Tim Ravgarden and many other people. It's like a few years old, and it's about this topic of beyond worst case analysis. And this is like a huge topic, right? So there are like 30 chapters in this book. Like each chapter trying like some kind of like a little bit different approach of like, what can we say about this beyond worst case analysis, right? Like, can we say that, I don't know, maybe my algorithm is fast on some distribution, or I don't know, like all kinds of approaches. But let's actually look at just like first few chapters, right? Okay, so first chapter, introduction. Okay, so let's not look at that. But the second chapter, parameterized algorithms. So that's something that like makes a lot of sense to me. Like if we try to go beyond worst case analysis, we just like think of some nice parameter, and we will basically like parameterize by our problem, also like by this additional parameter, and try worst case, not just with respect to input length, but also with respect to that parameter. And this is, by the way, what we already did with Dijkstra, because you can notice that we have been talking about number of edges and vertices, right? So this thing is already basically like not the classical worst case analysis, like just looking at input length. We already have like two things, number of edges, number of vertices, right? And then you can imagine like all kinds of other parameters, right? So let's talk about parameterized complexity. I don't know, maybe like this. Right, so like the parameters can be like all kinds of stuff. It can be, I don't know, some tree width, or maybe it can be just like planarity. That's kind of like a binary parameter, right? Like either you are planar or you are not planar. Or maybe like some kind of like silly parameter could be like, I look at my favorite graph, and like my algorithm is just like fast on my favorite graph and like whatever on the other graph. I mean, that's also like a silly parameter, like a concrete graph. Right? Like, of course, like the main problem with parameterized complexity is like how to pick the parameter, right? So, okay, so let's now go back to this book by Tim Ravgarden. Let's look at chapter 3, and it talks about instance optimality, and this is kind of like the main hero of this talk. So let me explain what instance optimality is. Instance optimality is basically like parameterized complexity taken to the extreme. Okay, so instance optimality. So instance optimality is like parameterized complexity where the parameter is like the input. It's like the best possible parameter you can have. And this is like something like so incredibly strong that this is like almost like laughably strong guarantee. Like you are not supposed to have this kind of guarantee. So let me maybe like explain a little bit like what it is, right? So if I have some algorithm and I claim that my algorithm is instance optimal, it means like that on any specific instance you give me, like any specific graph with some specific weights, my algorithm is as fast on that instance as any possible other correct algorithm, which is like so strong because this other possible correct algorithm could be something like check that this graph on the input is like my favorite graph. If it is my favorite graph, like output the hard-coded answer for my favorite graph. Otherwise, do something else, right? You can always have like these kind of silly algorithms that are just like, check that the input is my favorite input. I'll put the hard-coded answer. Otherwise, do whatever. And I'm trying to compare myself with those algorithms. It's just like, it can't be true, right? I mean, there cannot be any instant optimal algorithms because it's just like incredibly strong guarantee, okay? So that's unfortunately true, okay, so what I'm saying, like that, it's like really hard to get like literally instance optimal algorithms. But it's actually interesting that quite often you can get something which is actually quite close to being instance optimal, okay? And this is what we are going to do. So what we are going to use is a notion called universal optimality. And there, it's kind of like I'm instance optimal on the graph topology, but like worst case over graph weights. Okay, I will now write it down, and I will also write down the formal definitions because I think it's like very important to understand like what I'm talking about. It's like instance optimal on topology and worst case on weights. Okay. So let me now try to basically give like formal definition of instance optimality and universal optimality, just so that like the discussion is kind of grounded. Instance optimality, universal optimality. Okay, so what is instance optimality? Instance optimality, if like algorithm A is instance optimal, if now it will be something like that, there exists some constant such that for all other algorithms A prime, and like A prime is like correct algorithm for the problem I'm trying to solve, we have something like that. The time complexity, and also for every input, the time complexity of A on I is at most C times time complexity of A prime of I. Okay. So by the way, also like if you know online algorithms, this is basically just like what they call competitive analysis. Whereas in online algorithms, they care about like the quality of solution, that we are like competitive with respect to the quality of solution. Now we are like competitive with respect to time, right? So this is instance optimality, incredibly strong guarantee. And now what is universal optimality? So again, it will be something like that. There exists some C, such that for all A prime correct. Right, we kind of have to compare ourselves only with correct algorithms, because kind of algorithms that are correct on all inputs, because otherwise we would compare ourselves with algorithms like print42, which like it wouldn't make any sense. And like for all graphs, like time A and max over weights. Oh, sorry, this should be again GV. Okay, so basically we are like instance optimal on how the graph looks like. Like for any concrete like picture of the graph, we are as good as possible, but we are still like worst case over weights, right? So now can you like smile at me if it makes sense, and ask a question if it doesn't make sense? Okay.
So how are you distinguishing between counting time and counting comparisons or specific
Oh.
operations?
Okay, that's a great question. Like for example, like in the paper we actually like prove that there is like algorithm which is universally optimal with like both respects, like with both ways of counting the time complexity. But actually like in this talk, we will not be talking about Curie complexity at all. We will be just talking about like time complexity. And basically like each Curie like costs me like one unit of time. Okay.
So just to be clear, like after I fix my graph topology, the weights which witness the long running time of sort of like the algorithm against which I'm comparing to is not necessarily the same weight.
Exactly.
That define my weight.
Yeah, exactly. Maybe it is true that like there exists some weights for which there exists some like incredibly fast algorithm for these particular weights, and this algorithm will probably be something like check that these weights are like my favorite weights, and then like output the hard-coded answer. But like, you know, this algorithm will be very fast for concrete weights, but like for all other weights, it will probably be slow, right? So this is why we have this like instance optimal on graph topology, worst case over weights, because sure, we can have these silly algorithms that just like hard-code everything. So basically, if I want to compare myself with those silly algorithms, I need to say that they are slow on some other weights than the actual input. Everything makes sense? Can we go on? Okay. So the result that I want to talk about is that, okay, going back to this Dijkstra, right, and going back to this discussion, how Dijkstra with Fibonacci heap is in some sense best possible for this distance ordering, I want to say that some variant of Dijkstra's algorithm is actually universally optimal with, like, for this problem of distance ordering, okay, which is like much stronger guarantee. So the theorem is that Dijkstra is universally optimal for distance ordering I need to be a little bit careful about the model. It has to be like some kind of generalization of the comparison model. It is something called comparison addition model, which is basically like the model that kind of basically talks about what Dijkstra is doing. Like you can like add things together, like add weights together, you can compare them, stuff like that. But you are not allowed to like look at the fifth bit of some weights or something like that. You are not allowed to do some bit tricks. Addition model. Okay, but here comes like important catch. So the Dijkstra was like worst case optimal only with Fibonacci heaps, right? So for example, right now I need to tell you like what is kind of the heap that makes Dijkstra algorithm universally optimal. And it is actually not Fibonacci heap, it's like heap with some kind of stronger property. So let me write it down. If it uses a Fibonacci heap with the working set property. Okay, so the working set property, I will explain it in a minute, is like some kind of beyond worst case property for heaps. It's like relatively clean property. People are actually studying this property like independently on this result. And like what we are proving is like if your heap has this additional nice beyond worst case property, then Dijkstra also has this nice beyond worst case property. Okay, so does this theorem make sense? Modulo that I need to explain the heap, right?
So do you know that with the textbook Fibonacci heap, it's not universally
yeah,
optimal,
it is
or
not.
You
It is not.
couldn't prove it?
It is not. I can give you example in a few minutes actually, and that's actually great thing that I should do. Yeah, thanks. Okay, so I will now talk a bit about this working set property, and then I will try to basically like sketch a proof of this theorem, which is actually like pretty simple. Okay, so let's talk about working sets. Okay, so now we have to start talking about heaps. Okay, so what is a heap? It's like, or priority queue, I should say. It's like a data structure that supports like two operations, insert and extract min. I mean, for Dijkstra we also need decrease, but right now let's not talk about decrease. So just insert and extract min. Right? So actually, let's make some kind of example of like how can a sequence of heap operations look like. So maybe like the first operation to a heap is like insert element. Let's say it's like 1. So like the second operation will be like insert 3, then insert 2, and then let's say we will extract min. So in this case we would extract the element 1 because 1 is like the smallest thing. Then let's say we run next extract min, we would extract 2, next extract min would extract 3. Okay, so this is just like some kind of like dummy sequence of like 6 operations that I could do to my heap. On this dummy sequence I will try to explain what is working set, what a working set is. So first let me define what is like a working set of a concrete element x at time t. Okay, so I will need to define what this is. Okay, so this thing will be defined as like the number of elements that were inserted after x was inserted and that are still present at time t. let me write it down. Elements inserted after x that are still present at time t. So let's do some example. Like for example, for this element 3, I guess would be interesting one. So let's see like what are the working sets for this guy, right? So like before this element was inserted, this notion doesn't make any sense. After this element was extracted, again, it doesn't make any sense. So let's just look at kind of all the points in between, right? So at this point here, the working set is size 1. Let's say that like x is counted towards its own working set. So like after insertion, the working set is 1. After inserting this guy, the working set is 2. Right? Like the working set of this element at this kind of time snapshot is 2, because like this guy is still here, this guy is still here. After extraction of 1, it is still 2. After extraction of 2, it's only 1. Right? And like from now on, it's just like 0 or it doesn't make sense. Like we don't care. Okay, so this is a working set of a particular like data point at particular time. And the actual working set is like max of this thing over all times. So this is basically like looking at the time snapshot when this thing is like the largest possible. And I define this thing to be like the working set of x. Yeah.
Why? So here you're trying to compute the working set?
Yeah. So this example. So this example is like just concrete sequence of like 6 operations. I'm sorry that I didn't explain what this means. This is like I'm inserting an element whose size happens to be 1, and I'm these numbers are like the working sets of this element in like all of those time snapshots.
But why at when you insert 3 you have 1 and not 0?
Oh yeah, there is some kind of ±1 issue. The way I defined it, I should at like insert it after x. Including x, sorry. Okay.
Is part of your model that the elements themselves have timestamps and you're going to use the timestamps to break ties?
Oh, like if the question is that, for example, here, this is like not defined like uniquely, that there are like more time snapshots, it just won't be interesting for us because we will always care just about like size of this thing. So like I actually don't care if there are like 3 times when this thing is maximized.
No,
I
my question is, okay, so you simplified the notion of element because in Dijkstra's algorithm it would be a vertex and a distance.
Oh, I see.
And so 2 vertices may have the same distance, they're inserted at different times, and you have a choice.
I see. Yeah.
You extract
I understand.
You extract the one that was inserted more recently or less recently.
So there is like an implementation choice in Dijkstra's algorithm, and like my implementation will always keep every element in the heap like at most once, and like when you and basically I will implement things during like using this decrease operation. So basically like when the element already is in the heap, and now I kind of need to like open it like from another vertex. There is like another edge leading to that vertex. I will just use like the decrease operation on the thing which is already in the heap, if it makes sense.
That wasn't my question. My question is, you can have ties in the heap, right? So my question is, are you using the timestamp of when the element was inserted to break the ties?
Maybe like just for this discussion, let's assume there are no ties in fate. Yeah, I would have to start thinking about like whether this is important. Like probably it's not important, this issue, but yeah, let's assume there are no ties. Okay, but the definition of working set, does it make sense? Okay, so this is kind of like important thing like for this talk, right? But there is like still like one more important thing that I should say, and this is like what is working set property. What does it mean that like a heap has working set property? Right. So working set property is that basically the heap has the property that extract min of some element x takes time O of log wx instead of O of log n. By the way, this is kind of like stupid notation like extractmin of x. It's not like that x is like the parameter of extractmin. It's like if I run extractmin on the heap, it happens to return x. Then in that case, I want the heap to be like kind of faster than log n, right? I want it to be like log of working set and not log of n. And this is the working set property. And Fibonacci heap with working set property means that like all operations are constant except of extractmin that has this cost. Okay?
Sorry. Can you probably clarify for the audience what are the runtimes of
I should. Okay. Yeah, thanks a lot. I should do it. So like Fibonacci heap with working set. So this is like a data structure that supports like 3 types of operations: insert, decrease, and extractmin. So these are exactly the operations we need to run Dijkstra. Like in my implementation where every vertex is in the heap exactly once, or at most once. And kind of the running cost of these will be O of 1. And the running cost of this will be O of log working set. Okay? So this is like the data structure that I'm talking about when I am like, when I was stating this theorem, right? This one. This is the data structure I'm talking about. Like the first question is not clear whether such a data structure exists. So actually, there is like a long line of work on heaps with all kinds of working set properties. Probably like it seemed like that none of those heaps is the thing we actually needed. So we actually like proved in our paper that like such a heap exists. Like, such a heap exists like with like exactly this running times that we need, and with like exactly the working set property we need. So this is like the part of the proof of the theorem that I actually don't plan to talk about, maybe a little bit in the end. But right now, like what I want to focus on is just, given that this data structure exists, how do we prove this kind of result? That Dijkstra with this data structure is universally optimal. Okay? So now is again a perfect time to ask questions.
Have you implemented the heap?
Okay, we didn't. I actually thought about it a bit. Also, for example, if you know pairing heaps, this is like some kind of famous heaps that are like famously good in practice. They also actually have some kind of working set property. So actually, I kind of hope that like this result could be maybe some kind of theoretical justifications, like why it is a good idea to use pairing heaps in your Dijkstra algorithm. But like our construction is actually like the basic idea is implementable, but like with all the bells and whistles that are necessary, it's like horrible. And also, by the way, already Fibonacci heap is kind of like on the border of being practical, right? So it's kind of not clear, like if you have Fibonacci heap with like additional bells and whistles, like whether there is any chance that it will be practical for graphs that are smaller than 1 billion, or you know. Okay. So can I go on? Okay. So from now on, I just really want to prove this theorem. That's just like the only thing I plan to do in my remaining time. Okay, so we want to prove that the algorithm is universally optimal, right? So like what does it mean? So like the first thing we should do is like fix an input graph G, right? So fix G. So this is proof. Right. So like from now on, I will just be talking about some fixed graph G. Like somebody gives me a graph. And now there are like two things. There will be like some upper bound and some lower bound, right? Like on one hand, on this fixed graph, I will run my Dijkstra algorithm, right? So let's talk about like upper bound. Upper bound. So on one hand, I run. Actually, let me also like fix some kind of concrete input weights, right? So like somebody gives me some input. And run Dijkstra on this graph, right? And like the first question is like, what is the time complexity of this algorithm being run on this graph, right? This is like the benchmark we will then try to like achieve also like by a lower bound. So the question is, what is the running time? So what is kind of the time that kind of this algorithm, Dijkstra, this algorithm Dijkstra being run on this graph, right? So now we need to think a little bit about like what's happening in Dijkstra's algorithm, and actually really not much is happening there. Like everything is kind of like linear time complexity. If we are using our clever heap, all inserts, all decreases are constant time complexity. So there is like some kind of term like O of n plus n, which kind of like every algorithm that reads the input has to have this. And like what is kind of the only interesting thing happening are these extract min operations, right? So there will be like some plus sum of u in Vg log working set of u, right? So this is the complexity of Dijkstra. So basically, okay, this like finishes the part with upper bound. Now we need to talk about lower bound, right?
Just to clarify, this W is the number of discovered vertices, but not yet confirmed.
Yeah.
Yeah, so it's confusing because you're using W for two different things, the weights and the
actually, so you cannot see it, but this is actually capital W.
Okay, nice rest.
Yeah. Actually, I forgot to tell you like one additional like interesting thing, and this would be like this example, right? Like for example, like what is like the example of a graph where this algorithm is actually like much like substantially faster than normal Dijkstra. So actually, before talking about lower bound, let me just like give an example where this complexity is like better than n plus n log n, right? Just to like see that we are like talking about like something. So this example will be like a broom, I guess. So this is S, and the graph looks like this. And let's say that this number of vertices is like, I don't know, like root of n, and the number of vertices here is like n minus root of n. Okay. So first of all, this graph is just a tree. Okay. Like computing distances on a tree is very simple. So it's like really important that we are talking about distance ordering and not about computing distances. Like, very important, right? So second, actually, if you run like Dijkstra's algorithm on this graph, like can you like tell me like what's roughly going to happen when you just run Dijkstra from this vertex on this graph?
Well, depending on the weights on the left side, but
Yeah. Oh, but actually, it kind of doesn't really depend on those weights, because like when you start in this vertex, you just like put everything in the heap, right? You don't even care like what are the weights, you just like put it in the heap. And from that time on, your heap has root n elements. Which means that like, if we don't have additional worst case, beyond worst case guarantees, like regarding that heap, actually all the operations from now on cost you log n, right? Because like the heap is huge in some sense.
why?
So
What's preventing them from being extracted very early on if these weights are very small?
Sorry, pardon. You are actually totally correct. Yeah, I mean, if these weights are very small, then actually Dijkstra would do great, because it would just like put them on, it would extract them, and basically, okay. So let me just like quickly say like, you know, it will turn out that like for some kind of bad weights, the running time will be like n log n for normal Dijkstra, whereas for our Dijkstra it will be more like t. Okay, so this is like t. It will be more like t log n plus n. Right, and basically like what you said was that like, okay, if these weights are very small, then actually even t log t, it's the same thing, but yeah. So basically what you said, like if these weights were very small, then we would like spend t log t time on like handling this, and then just like linear time going on. Unfortunately, if the weights are big, then we just like insert them into our heap. Our heap is huge from now on, so now we are just like going through this path. Each time we spend like log n time on extract min, and we just like spend this time. Okay, so this would be like the normal Dijkstra. Okay, whereas this is like our Dijkstra. So can you actually try to like give me tell me what is the reason why if we run our Dijkstra with like this clever heap, why the complexity is more like something like this instead of this? Yeah.
Because when you're going on the right, you're looking at each thing small.
Yeah, yeah. Mm-hmm. Yeah, basically, like if you imagine that like you just like insert all of these things in the heap, like this is like the first thing you do, you just like insert these things in the heap, right? So now like from the perspective of these vertices, like when you are just like riding along the path, like the working set of these guys, this is just like 1 or 2 or something like that. Like these guys, they don't care at all about like what happened here at the beginning of the algorithm, right? That's like one nice part of this working set definition, that like these later guys do not care about past. But like the other nice part about this working set definition is that like these guys actually also kind of don't really care about what's happening here, because like from the perspective of this guy, like maybe like the working set of this guy is like t, because there's like t other things that we inserted. But like what's happening here is always like insert, extract, insert, extract, insert, extract, right? Like at any time snapshot, like the size of the working set is like basically the same. So actually these guys are also kind of happy. It's not so important for these guys because like difference between t log and t log t is actually in this example that there is no difference. But yeah, so this is like kind of the intuition, like why this working set property is like exactly what we want, right? Does it make sense? Okay. Yeah. So this was not part of the proof, right? This was just like an example. Like going back to the proof has some kind of upper bound, lower bound, right? Somebody gives us some input. We first run our Dijkstra algorithm. We notice that it has like this beautiful complexity. We basically don't care about these linear terms at all. We just care about this like sum of log of working set sizes. So now basically like the whole game is to try to construct like a different weights such that or like weight distribution, so that we say that like any algorithm being run on this weighted distribution needs to spend at least this time, right? So basically, if we go like all the way back, if you still like remember this picture, so this picture is like the picture that kind of like proved that the Dijkstra with Fibonacci heap is like worst case optimal. Like in this picture, basically like formally, what we did was that we said, oh, if we kind of construct like a random distribution over these weights, then this is like uniform random permutation over these vertices. Like you know, like their order is like uniformly random permutation, and like any algorithm that like sorts n numbers that are like uniformly randomly permuted needs to spend n log n time, right? So like formally, basically like what was happening here was that there was some like hard distribution over inputs, and we said like every concrete algorithm has to like kind of expected complexity of that concrete algorithm on this hard distribution is at least n log n. So this is what happened here in this picture with star, and we kind of want to do the same thing, right? So what do we want to do? So let's talk about lower bound. So we have like this concrete graph G with some source S, right? This is like the graph that is already fixed. And what we like want to do is we want to kind of like partition it into some layers. And then we want to like repeat the argument for the star in each layer. We kind of want to say like, look, any algorithm that solves distance ordering on this graph, it kind of solves a sorting problem here. It solves a sorting problem here. It solves a sorting problem here, right? Because like we can construct such a weight so that if you order these vertices by their distance, like first you will see only these vertices in some order. Then you will see these vertices in some order, and so on, right? So this is like the weight distribution that we are going to describe or construct, that basically we kind of force you to solve sorting here, right? And because we can use like sorting lower bound for each layer, then like this kind of argument can give us a lower bound of omega sum of ti log ti. Actually, t is not used for anything, right? So I guess I can use it, where ti is the size of the ith layer. Right, so this is like our general strategy, and now I'm already like not so formal. I didn't tell you like exactly what is the definition of a layer, but I hope it's like kind of clear that like the only thing we want from this layer, like from one layer, is that like each two vertices are kind of like incomparable. That like if, for example, like if the graph looked like this, I don't know, then like these two vertices cannot form a layer because you always first see this one and only then this one, right? So like in a tree, like layer is like a set of vertices that are incomparable, right? In a general graph, like I claim that there is an underlying tree in which these layers are incomparable. And also like every two layers the layers needs to be kind of like sequentially, right? It's like sequential after each other. So basically I claim like when I say like construct sequence of layers, basically like what I'm saying is like there exists some weights that force you to first see all of this, then all of this, then all of this, and so on. Right, so let me not try to write it down formally because I would just get lost. But I think that like from the picture it's kind of clear what we want, and I hope that it's also kind of clear that like once we do it, we get this lower bound. That like really the hard part is like that here we have some TIs that we somehow like get by some procedure from the graph, and we don't know how to kind of connect these TIs with our working sets. That's like the hard thing, right? Okay. So if this picture like still made sense, let's continue. Right. So somehow like the whole game, or like from now on, like what we need to prove. What we need is just like construct layers. I identified it formally, so that sum of Ti times log Ti is at least sum of the sizes of working set. Actually, look here. Okay. Like, can you smile at me if this equation still makes sense? That this is basically like until the rest of the proof, we are just talking about this equation or this inequality. Okay. Okay. So how do we construct these layers, right? So let's just like try the simplest thing possible. So constructing layers. Constructing layers. Okay, so let me first tell you like how we find the layer number one, like the first layer. So the first layer we find just by saying, look at the vertex with the largest working set, and the working set will be the layer. I will now try to like draw some picture and like explain like what we are doing. Okay. It is the working set of U1, which is argmax W U. Okay. So let's actually try to draw some picture and try to understand like what's the intuition about like what is a working set of a vertex in a graph, right? Because now we have like this property of heap and this property of Dijkstra's algorithm. It somehow like relates to each other. So like basically somewhere in the graph I have this vertex U1, which is the maximizer of the working set, right? And like what does it mean? So first of all, like this definition of working set was that like working set is like the largest working set like wxt for some time t, right? It was like that was like some snapshot when this working set wxt was like really large. So basically what it means is that there exists like some kind of like time t, I don't know, like time t. And when I look in my heap at time t, I am seeing U1, I am also seeing like a bunch of other elements, right? So when I'm running Dijkstra's algorithm until time t, and then I look at what is in the heap at time t, it's kind of like a layer, right? It's like basically the algorithm like goes like this. It's kind of like explore some kind of ball, and like at every time, like what the algorithm has in the heap is kind of like, you know, like a boundary of a ball or you know something like that. So basically, if you like imagine that like, you know, maybe these are like the vertices. This is like what Dijkstra has. Dijkstra has these. Dijkstra has these vertices in the heap at time t. Right. So that's already nice because like my working set Wx is like a subset of this nice layer-like looking thing, right? So like W1 is like a subset of what Dijkstra has in heap. In heap at time t. Okay, so maybe like this would be, this smaller thing would be U1, right? So this is like the working set of U1, and it's like kind of like a nice set in the sense that it really like looks like the layer. I didn't define it formally, but basically there are some weights such that if you are following these weights, you will kind of see all of these things like at the same distance, basically. Right? Okay, so actually in this particular case, this picture is a little bit misleading because it turns out that U1 is like already the whole thing. Because if there was like some other vertex here, that would not be in U1, I could ask like, what is the working set of this vertex at time t? Like, why is this no vertex in the working set? Well, because it was inserted even before U1. But it means that like all of these things are in its working set at time t. So actually, in this case, and it's not like, in the actual proof, we are actually not using this property, but I think it's like very intuitive and kind of helps understanding. Like in this case, when we take the first layer, it like literally just like splits the graph into like left part and the right part, and it's like this like beautiful layer, and like going back to like this lower bound idea. This is like one of those layers that we use in the lower bound. We are like forcing what we will do is like we will force the algorithm to solve a sorting problem on these vertices. And what does it mean, right? So if we kind of try to like connect what we are doing, then like we just found a layer of size W1, right? And what does it mean for us? Like when we force the algorithm to solve a sorting problem on this layer, this implies like the lower bound of W1 times log W1. Okay, so like is this, okay, so we got some kind of lower bound here. Is this like a good thing or a bad thing, or like what do we want to like compare this with? Like, are we in business or not? Okay.
Isn't this just the TI log TI thing?
Oh yeah. So here this thing that I wrote, this is just like this TI log TI, for TI being this, because like the size of this layer is this. So what I now wanted to say is that like, we have like this lower bound, and like for these vertices, we can kind of embed a sorting problem on them that like that gives us like this kind of lower bound. We also have some upper bound, right? It would be great like if lower bound matches the upper bound. And like what is the upper bound, right? So if we go like all the way back, the upper bound is this, right? So what the Dijkstra is actually paying is like the sum of log working set sizes. So going here, so we constructed some lower bound, and like Dijkstra is paying O of sum of four vertices in that layer. Right, so what I'm now doing is that like I constructed this layer. This is just like some set of vertices. On those vertices, I achieved this lower bound. Now the question is, what is Dijkstra paying for those vertices? And it is this thing. And now actually, if you look at this thing, then, and if you okay, so now it's time to use the assumption that we picked U1 in some way. We picked it to be like the largest thing, right? The thing with the largest working set. So we can actually say that like this thing is at most, the number of vertices in that working set times log of W times log of that working set, right? So this just follows like from how we picked U1. And that's amazing, right? I mean, so this is our upper bound. This is like how much we are paying for these vertices in Dijkstra. This is our lower bound. This is like what is the complexity of the problem that we are embedding in this layer. Just like the same thing. So like the lower bound matches the upper bound, and the rest of the proof is just that we just like continue doing this. that we just like, after we found the first layer, we say, let's like kind of do the same thing to find a second layer, third layer, and so on. And you know, we need to check some properties. We need to check that these layers are really like these nice sequential things. This kind of just follows from the fact that each layer is just like a snapshot of like, at time t, if you look at what Dijkstra has in the heap, it's like some kind of like nice like boundary of a ball that is growing, right? So like all of those layers that we will be finding, they will be just like nicely sequential. And like in the end, after we finish, we will have kind of, every vertex will be in a layer, lower bounds will be matching the upper bounds, and we just like paid for everything. Okay, and that's like, this is like the false version of the proof, or like the actual proof is a little bit more complicated. And now the question is, either I will just lie to you and I will just lie that it is like that easy and we will finish the talk, or if you want, I can tell you what is like the one more problem that we need to solve for the following layers, and then we finish the talk. So basically it's like up to you, right? Also, like if I have 5 minutes, I can talk 5 minutes about how you construct the heap with the working set property. So, or if you have any questions, now it's again a great time to ask questions. Okay. Yeah. So I have 5 minutes. So maybe one other thing that I can do is just like try to like zoom out a bit, right? So, and then we will finish. So let's go back to the very beginning, right? So I have been talking about this problem of distance ordering, about Dijkstra's algorithm. In some sense, like the thing that we have proven, it's like maybe not so impressive, because like this thing is already like so close to linear time. Basically, like the whole talk was about finding just this one log n. It's kind of like stupid, like n log n is already like almost n, right? So in some sense, like what we got was that like, okay, sure, there are some instances when you can do better than that, and in these instances we are really like getting like all the juice out of like how the graph looks like, and we are getting better than n log n, but we are not getting that much better, right? So maybe like the thing to take away from this talk isn't really like this concrete problem. Maybe it's more like this notion of this like instance optimality and universal optimality, which I think is like really an amazing notion. And actually, like on the first glance, it seems like you can never achieve it, right? And that's kind of true. You like almost never can achieve it. But it seems to me that like it's like a nice thing to have in the back of your mind, that like this thing exists, and like you always want to check like whether you can achieve it, because if you can, then it's like really amazing, right? It's like the strongest possible guarantee that you can have about an algorithm. It's like really cool. So for example, this universal optimality, it's like coming from the area of distributed algorithms, where it was actually very successful, because in distributed algorithms, it turns out that you always have some kind of like weird graph on which your algorithm like has to be slow because of some stupid reasons. But in practice, like all interesting graph classes, like planar graphs and so on, are like much faster. And so this is like what motivated this universal optimality in distributed algorithms. And in general, I feel like that it is like a nice notion, and it's also nice that it seems like you can build some kind of like theory behind this, like beyond worst case analysis. Like, you know, this heap with the working set property is just like a property that was studied like long before us for heaps, right? Because it's just like a nice, clean statement that you can make about heaps. And this universal optimality of Dijkstra, again, like a nice, clean statement that you can make about Dijkstra. So it's like nice to see that there is like some theory behind this, right? That there is like some way how these things relate. And like if there is like something to take out of this talk, it would be more like this general vibe than like the concrete results that we construct some layers and so on. Okay? Yeah, so that's it for me. If you have any questions, I will be happy to try to answer.
Questions for Russia?
So what if I don't care about ordering?
then like actually we don't have lower bounds, because as far as we know, like the complexity could be linear. Actually, there was like recently this like really amazing paper that proved that actually you can, if you don't care about ordering, you can do like m times root log n. So you can actually like improve, even in this comparison model, you can actually improve beyond log n. But like nobody knows like any like other upper bounds or lower bounds. So it's just like completely unknown like what's happening there.
How can I find that root?
Actually, I think so you know, it was like one of the things that I planned to talk about, because and then I forgot about it, but it's this paper. Yeah, I'm also sorry that I forgot to cite everybody, but basically, like there is like this long line of work on heaps, right? Which in the end we like didn't use, but definitely like working set is not like the new thing. Like there is the work of Iacono, the work of Elmasri, and like many other papers that build the theory of heaps. Fibonacci heaps, it's also from Fredman and Tarjan. Yeah, so maybe just look in the paper for citations. Okay.
I think there might be people working outside trying to use that.
Okay, so it's great time to finish.
But,
Okay, thanks.